So this is going to be probably quite a long, very casual, probably sloppy video. Quantum stuff beyond the course. And the course that I'm referring to is first year chem. So it's become normal that certainly in university first year textbooks, where you go over trends in the periodic table and quantum numbers, they show you the particle in the box, they show you the complete solution to it. They even show you the solved solutions of the hydrogen atom itself, they show you the wave functions, etc. So we've reached a point where first year university chemistry definitely lets you take a look at that. Now, here at the college, I don't specifically teach or hold the students responsible for that content. So what I am going to do is give a brief overview. This is not in any way, shape, or form meant to be an instructive video. It's meant to give you sort of a decent enough overview so that as time goes on and we take up more rigorous solutions in third year physical chemistry, you'll already have a pretty good idea, almost like a preview of some of the general concepts. And it's completely up to you if you want to even use your first year textbook and go into it deeper, because it is there. And this camera has a trouble going blurry. So let's see if this is going to help it or not. Have to keep an eye on that. Okay, so this all starts with the Schrodinger equation, and the one that we use looks like this. For all intro courses, it starts out like this. And if you go online, so this one is time independent, right? So if you look online, you're going to see one that's it looks much fancier, and it's time dependent. So this one, what we really want to do is demonstrate how the birth of a quantum number takes place. So what we're going to do is choose one of the simplest possible models of all. But before we get into that, we want to say just a couple of things. This particular Schrodinger equation, the Hamiltonian, this is an operator. They put a little hat on it. And this right here, which is called the wave function, so if you think back to math class, where you could have, for instance, a parabola, and then they might look at this and they'll say, okay, y depends on x, but they could say y is a function of x. So this is where they will talk about this relationship like a function. One of the variables depends on the other. So this is the exact lingo that we're talking about, the wave function. This is just a mathematical function, depending on the model that we're going to go ahead and take a look at. The interesting thing about the wave function is, and we need to know this right off the bat, the wave function itself has no direct physical interpretation. So one of the things that you might remember even in high school textbooks is they start talking about a wavy thing. They may even talk about how at one point in time surrounding the hydrogen atom, Bohr understood that you needed integer numbers of the wave. So when you see this, and previous to this image, you see stuff like this. You see the picture of an atom like this, and you see it as this. Or you see other pictures where the Bohr-Rutherford model put the first two electrons here, and then they filled them in like this. So you're seeing planetary orbits, and you're seeing images of an electron. All of a sudden they show this. But what they don't make crystal clear is that this idea of a wave completing a circuit around a circle, as an example, and we can get to this as particle on a ring model coming up shortly. One of the rules of quantum mechanics is this wave function, this mathematical function, is essentially what we're saying is it's not allowed when it comes back around. It has to repeat itself. If it doesn't, and let's say it gets a little bit out of phase on its second way around, well then you're going to get two values at the same point for the wave function. And that has no possible observable outcome sense. This is not the path of the electron, folks. When you start talking about wave mechanics or quantum mechanics, any images of a graph that looks wavy, you need to stop right there and say, these are totally and completely wrong, and it'll set you back. So you have to understand that the wave function essentially contains all the possible observable outcome information of the system. Okay? So what that means is, this is called an operator. And one way of people, I'm loosely saying this, don't take it too literally, but so if this is a magical math function that we have successfully built to contain all the observable outcome information of our system, the wave function has no direct physical interpretation of a particle moving as a BB in any way, shape, or form, not directly. We can ask it questions to pull out some of the answers of observable outcomes, and this one is asking questions about the total energy of your system. So this asks this a question. This equation, I forget how they call it, eigenfunction. This is an eigenfunction, eigenvalue equation. Those are the types of words you'll see much later. But the point is, you ask it a question mathematically, perform a mathematical operation on it. You will get the answer to the question, total energy of the system, and you need the wave function left intact. And it took an army of people to mathematically come up with this mathematical machinery. And this is exactly why historically you may very well hear people saying that quantum mechanically, they often say shut up and calculate, which means just trust the math as a tool to give you answers of observable possible outcomes. The wave function itself and the mathematical machinery and why you're doing it, it's not as if it's crystal clear and there's no physical interpretation of it in the first place. So you have to accept that. And you have to keep saying it to yourself. The wave function, anything we ask it are questions. We get answers to what could be observable. So the other things that you could ask, for instance, P stands for momentum, put a little hat on it. This is an operator that could ask an acceptable, you have to go find it, wave function to properly answer the question. You can get answers to what the allowable momentum values are. You could even say the position one. If I'm only in one dimension, it'll be X, okay? But if you're in 3 dimensions, you're going to have something that's a combined operator of the X, Y, and Z, for instance. But if it's 1 dimension, you could say, where are you? This is the position question operator, okay? So this is the idea of how this works as a mathematical tool. Do not think the wave function has anything to do with, in our case in chemistry, we're going to love to start talking about, as an example, an electron as our little particle, because electrons are what's on the hydrogen atom, and we talk about electron configuration. So that's coming. So how are we going to demonstrate this? Well, we can start with the classic, in all of introductory level quantum mechanics, one of the first models that's always used is particle in a one-dimensional box. Now, for our purposes, just as an example, this can apply to any type of particle. It could be a proton, you could use an electron, you could use an entire helium atom. Heck, you could even use a carbon-60 buckyball as your big particle in a box. So the same thing applies to the particle, but we're going to start with an electron, and we'll say, let's just put an electron in a one-dimensional box. So what does that mean? Well, in math class, when you look at a Cartesian coordinate system, and somebody could say, see this x-axis? What is the thickness of it? And you'd say, well, it's infinitely small. It has no thickness. So when we talk about a one-dimensional box, we're gonna bend the rules a little bit. We're gonna say, let's pretend that you have a magical hose, and this hose can hold an electron. So we want to put an electron and trap it. So let me just go back for a quick second. What I should have mentioned here is the one thing about quantum mechanics, and I've said it before in previous videos, but I almost call this my own personal. This is not real. I am using it as my personal zeroth statement, characteristic. In order to have quantum effects, you have to have boundary conditions. You have to have constraints on your system. You have to have a trap. You have to have a box. You have to have containment. And I think we get the gist. If you had a perfectly, totally free electron with none of these, you would not see any observable outcomes. You would not get allowable values of it. So the fact that you put something into a boundary constraint, whatever, and it doesn't matter what type of box, you could even say, oh, let's make a tiny little, I don't know, 10 nanometer square box. Oh, let's make the diameter of a little sphere, let's make it 10 nanometers, and we'll put the electron in here, or we'll put it in here. See how these are two different shapes of containments? You will get different allowable energy states. You will get different electron density pictures in either of these. You could even trap it to float around a positive charge. These are what I call boxes, constraints, boundaries. This is the model. You could even say one of the models is, let's have a sphere, but let's trap an electron on the surface of the sphere. Very different than bounding it inside a sphere or inside a perfect cube, or how about a longer sort of cube-like box, rectangular, right? So those are all examples of how you could box and constrain it. And the zeroth law says without containment, you're not going to get the only two things that the biggest, like bing, bing, like the two biggest things talked about in introductory quantum mechanics is you bound a system at the small scale and you get allowable energy states. And our math toolbox will allow us to calculate surprisingly accurately the allowable energy states, right, which is pretty big. How do we test this? Well, if I had 3 energy states, just for instance, the first 3, well, this is an energy difference. I can calculate the energy of the states. It's the difference, and we can throw a photon at it that matches this energy, and we can measure this experimentally. That's the proof of us using the math to shut up and calculate this, check. And then secondly, if we threw an electron or a proton or a particle in the box, we can get images of the orbitals, which is the shape of the electron density. The spread outness, the particle itself, when you leave it alone, if you will, ceases to exist as a little BB moving around at all times. Been proven 6 ways from Sunday that something funky is going on where it seems to spread itself out, and hence the latest word is, one of the latest ideas is, look, when it's in quantum superposition of all the positions it could be found in when you look, when you're not looking, you get sort of the quantum field. We all know that fields, much like a bar magnet, north, south, you know these magnetic field lines? There's no BB, but you know that the energy of the magnetic field, and when you put a piece of white sheet of paper on top of the bar magnet and put iron filings, you can see the magnetic field lines. See how continuous and spread out they are? And it's very real. So this is what they're saying. When we're not actually interacting and looking to find an observable outcome, which is the tiny electron, for example, and where it was, you look away, it goes back into superposition of all the potential positions you can find it. So literally it spreads itself out, stops existing as a BB. It's part of the quantum weirdness, but these are the two things. The main, in introductory quantum, the main two things we always talk about are a big deal: energy states and the shape of the orbital or the electron density. So that being said, we're working on a model where our containment is a hypothetical, and we're going to say let this be the x-axis. So let me just get rid of that. We know we put an electron in here, and we're going to say it's from 0 to L. And this is the x-axis. So what we're going to say is, in physical reality, are we going to say that the electron was some kind of radius? Can I really use just one dimension only? It's got some thickness. We're saying, look, pretend that doesn't exist. Let's pretend like an ideal gas law, right? You know, and somebody says an ideal gas law, volume versus temperature. When you go to absolute zero, oh, it goes to zero volume. Well, we know that's not real, but this is a model, a theoretical perfect gas model, and the little particles are infinitely small. Therefore, at 0, they have no volume. We bend the rules a bit, because it's a model. We'll do the same here. So pretend it's a perfect one-dimension x-axis box tube for the electron to fit in. We're going to trap it. So a lot of the books are going to show an image like this, and they're going to show the potential energy is infinite outside the box, and inside the potential energy is 0. So me, being a novice, I used to look at this and I'd say, oh my God, this looks like a box. And I thought it was one dimension. I'm so confused. Well, Atkins does a great job at basically saying, look, by the way, don't think this is a two-dimensional box. The box is the one-dimensional 0 to L. The infinite potential energy is our way of 100% guaranteeing that the electron has to be trapped between 0 and L. Infinite potential energy, well, means it can't get out. So what's in there? This is our x-axis. So now what we're going to do is we're going to say, look, the Hamiltonian energy question operator of our information containing math function of the system we're going to build, E is the answer. So basically put, this ends up being, you take two derivatives in a row. So with x only, you're going to take the second derivative. I'm not going to show you this. You can look that up if you want, but I want to get right to how you witness they take the time to find an acceptable function that could satisfy some of the initial parts of the questioning of the Hamiltonian. So what they do is they're looking, and this is a process, they're looking for an acceptable wave function. They get to a point where they're saying, look, I could put, I don't know, a constant a in the front, sine, and some constant that might exist. This looks like an acceptable function. So now, with our little particle trapped in this box, 0 to L. And we could call it y for now, but we could call it better, I should call it the wave function we're looking for, is this at the moment. So what could k, what do these boundaries dictate to what k, this constant, math constant, has to be? So this is where they say, look, we know one thing. The value of this wave function we're working with, the value of it when we go to x equals 0 at this boundary, it has to go to 0. Now, what do I mean by this? One of the other big pillars of quantum mechanics is Born interpretation. And basically, if we had one-dimensional wave function, he came up with, when you integrate and square, so take the function once you find it, multiply it by itself, you know, they're going to have this little star thing, and that means if you have an imaginary number in your function, you replace it with negative I. It's a complex conjugate. And that's not important at the moment. The real meat and potatoes is you square your wave function and the integral. So if you squared a function and it was in math class, you could still graph it. And if this was the square of some math function, the integration over, for instance, the space you're integrating, let's say it was from 0 to b, you get the area under the curve. That's what this means. And basically put, the closest we can get to physical meaning from Born interpretation was, when you square it, find the area under the curve in the dimensions of the model that you made, we'll set it equal to 1. You're setting the area here to 1 because this is a probability. That's what that stands for. So for instance, let's say that you took this function, you squared it, you found all the area, set it equal to 1. Okay. But then somebody says, okay, now what I want to do is I want to go look from, this was 0 to b. What if I was at point 2b to point 3b? So that'd be like, here's the half, here's 0.2, here's 0.3. So this is 0.2 to 0.3b. Once this is worked out, you can say, look, if I integrate and find the area here, what percentage is this area out of the total of 1? So let's say this came out to be something like, I'll just make this up, 0.16. Guess what this means? The particle you trapped in some type of one-dimensional box, we haven't looked at the wave function yet, but if this was the graph of some other model we were looking for, if it was, the Born interpretation says, if you went in this box and you looked for it between 0.2 and 0.3b, your chances of magically finding it there would be 0.16, which is 16% chance. So do you see how squaring the wave function is so important, because it at least gives us some physical way of reaching into a box, looking in this area. And when we do that many times, we find out that it matches, the percentage of the time we find it, matches exactly what was calculated. So this has some complete validity to it. The wave function by itself contains nothing but the information of the system. As soon as you square it, you at least get an idea of the electron density and your chances of finding it there. So it's one step closer, but not a good physical interpretation. So that's why we go back here and we say, if I'm 100% sure that there's no chance to find the electron at 0 or L, if I'm going to square it, I need to come up with a 0 chance. So in other words, I need the wave function by itself, the informational thing. When I put 0 in of the box here, the value of this function has to be 0. So then we think to ourselves, okay, if I put in a 0 for x, we know that the sign of 0, because this would make it 0, is 0. So this function is okay at the moment. So the next question is, what happens at the other end? The same thing. The value of our wave function, if it's acceptable, has to go to a value of 0 at the boundary L, length of the box. Has to be this. So now to answer this question, we say, okay, now we're back in like math class, and hopefully I can do this without butchering it. So now back in math class, you say, oh, remember, oh, I don't know, let's just make up math class sine AX, right? The easiest one to start out with is if B was equal to 1 and A was equal to 1, you would graph the classic y equals sine x. And we know that in this case, you have a 1 and a negative 1, I believe. And my calculator said, this is how embarrassing it is. I get close, it's 0. And then I know, and this is pi by a half. This is the other 90-degree thingy, 3 pi over 2. So, yeah, the sine of 90 degrees is up here, and then the sine here. So the sine curve goes like that, right? So what do we know about this? What is it going to take? What is it going to take? I'll rewrite it here. What is it going to take about this that demands the sine function overall goes to 0 at the L value? So we know that the sine function, when you have integer numbers of pi, so here's 1 pi, 2 pi, and it keeps repeating. So at integer numbers of pi, the sine of integer numbers of pi equals 0. So in other words, I need, and then what we did here is we said, look, if we put in L for x, we need KL to be equal to integer numbers of pi. So therefore, we just witnessed the birth of an integer quantum number for a particle in the box, because our informational math function, which has no direct physical reality interpretation that we're aware of today, you have to trust it will magically contain all the information we need for observable outcomes of an electron in a box. And we know that we just witnessed the birth of the principal, well, the quantum number for this system. So I guess I could say K has to equal this. So we just witnessed as us making an acceptable wave function, we get this. Now, how do we, so this, folks, was what I really wanted to show you about a particle in the box, and I'll show you the more important energy level, or the orbital electron density in a minute. But first, the purpose of this A goes back to what we said here. The Born interpretation says the probability, and as soon as you have a wave function, you square it. You could graph the square if you wanted, but the point is the area under your squared wave function, which is the space of the box, you're going to set it equal to 1. So that anytime you calculate a different interval, 0.2b in this case to 0.3, your answer, for instance, if it was 0.16, is if this function has been normalized so that the square of it, the total area is 1, that's a normalized function, then this answer tells you it's 16% chance of finding it there. So the key of this is a normalization constant that makes this area equaling 1 true. If you did that analysis on this one, you would get in a box the official function for a particle in a one-dimensional box. There's your constant to normalize this squared function area under the graph. And then one of the answers to our questions is the energy, the allowable energy for a particle in a one-dimensional box is this, where n can equal, this one starts at 1, 2, 3, and on, go. So the mass of the size of the thing you put in plus the length of the box is crucial to give you the allowable energy states. So you could say the first energy state for an electron in the length of a box, if it was 10 nanometers or something like that, you could calculate the energy spacing. So remember what I said, quantum mechanics, this is messy. My personal zeroth statement that I keep saying again and again and again is I need boundaries, and I need to model what my boundaries look like. If I do that and I apply the quantum process of slowly evolving and finding and massaging an acceptable wave function for the system I modeled, if I do that, I will get two of the biggest things, the allowable energy states and arguably the shape of the orbitals. Now, the shape of these orbitals comes from Born's interpretation where you square the wave function, you map out the probability density over the box that you're in. That's the orbital. Spread out electron density. Those are the two things we get. So let's take a look at that for the particle in the box. This is a classic sort of diagram that I write for a one-dimensional particle in a box. On the left-hand side of the page, I'm going to give a sketch of the wave function. On the right, we'll do the wave function squared, which is the Born interpretation. This is the one that gives you a closer to our observable physical reality interpretation. The square of the wave function has a little more meaning to us. The wave function by itself, nothing more. Don't look at it directly and think, oh, it's the BB moving like this. No. This represents a math function containing information we can get out. So down below, if your particle in a box 0 to L wave function had n equals 1, the shape of it would look like this. If you square this, you get a little more of a height to it. Nothing interesting there. But what's interesting is as soon as you go to n equals 2, which is the second allowable energy state, you get a node. And the wave function looks like this. Your informational math function looks like this. Okay? Square this. These negative amplitudes will flip up, and it looks like this. Okay, now I'm back. So now, what this tells you, and this is where the interesting thing comes out, you have to start trusting the fact that when your electron in a box like this, if it's left alone and nothing is interacting with it, in a certain period of time, and it can calculate the time evolution. If we included time, you could evaluate the time evolution to come back to this spread out quantum field-like format for the electron. But Born interpretation says, if I was to reach into the box and it's in a second allowable energy state, and I looked right in the middle, my chances of finding it are 0. If we stay with the more classic way of thinking of an electron as a BB, how does it get from here to here? 50% of my chances are here, the other 50 is here. 0% chance in the middle. My greatest chances are sort of looking in here. Well, but think about it. That would be us assuming the BB is always there moving. And it's been proven that it's not. it actually seems to spread out into what we're not even 100% sure of, but we know it is no longer a chunk of mass always there in the way we see a basketball moving around. We have to accept that. This is an image of the electron orbital probability density. So if you could, if I was to draw a picture of that orbital, I guess I would have to do this. There's a node, n equals 2, this is 0, this is L. I could color code darker color here getting lighter as I go here, darker color here, lighter color as I get there. So the shading represents the electron density spread out in the box. And what's interesting is when you carry this one step further, two-dimensional. So let's say that you now make a literally a two-dimensional box and you add a dimension like this. Well, it turns out that each of the x and the y has an exact particle in a box style equation of the one we just did. So if n was equal to 2 in the x direction, you'd have one node, and the square of the x1 looks just like we showed. And in the y direction, if the y quantum number was 2, you have a node, and the square of the y part of the wave function would look like this. So this is your box, and you know that the particle's somewhere in there. This is a nodal plane, this is a nodal plane, and you see how this matches up with this. So you get the darkest density in the middle, and it tails off, right? The other classic way of showing this to really get the effect is your box would look like this, and you would draw these sort of like sand hills, if you will. This represents the shading of the electron's orbital here. You would never find it here, and your greatest chances are in the centers of the quadrants. I can represent the probability density with the third dimension being used to show you your best chances of where to find it. Okay? We're not in 3 dimensions yet, and then of course, if you wanted to, you could legitimately go to a full-blown 3-dimensional particle in this box. So let's say you took an electron and this was, I don't know, maybe 20 nanometers or something like that, cube. You'd have the x, you'd have the y, and you could have z out the back. You throw the electron in here, now in the 3 dimensions, you will get a picture of an orbital just like you've been taught for a hydrogen atom. You know, you get the s and the p orbitals. Well, inside here, for the different allowable energy states, you'll have a different shape of the electron density in this box. That's an orbital. Back in the 1 dimension, the best we can do is do darker shading if it's n equals 2, where you're going to find it. And you can see why in the second one, in a 1-dimensional box, you don't actually have the extra dimension to show the orbital density. You don't, but so that's why you get used to this. So that covers particle in a 1-dimensional box. We have, now what we can do, now what we're going to do, now we can move on to particle in a ring. So we just finished with one of the first classic types of containment containers so that we can quantize stuff, particle in a 1-dimensional box. Now we're going to move on to particle on a ring. And there's a couple of reasons for this. You can imagine a hypothetical ring, and let's say that we already know that at the quantum level, drawing a picture of a BB as an electron constantly being there is you got to be careful. We're going to draw it there when we need it so we can talk about it in partial classical terms because we have nothing else, right? But then to start talking about something. When we look away and the system goes back to superposition, we can know that little BB will cease to exist the way we think it's always there. But let's say it's moving that way and it's rotating this way. So unless I'm wrong, I have no idea. If the momentum vector uses the right-hand rule, if that's true, then you would have what a lot of folks will call momentum. We'll call it J. I'm thinking on the internet now, sometimes they use J, L, and S. Anyway, this would be very like in physics if you have a bicycle wheel, okay? Say a small bicycle wheel and you had a rod. And then you are going to hold, the rod, and somebody's going to spin this wheel really fast. And then they tell you to try and tilt it. And you're going to say, oh my gosh, it took quite a bit of force to change the orientation of this rotational axis. And that's when physicists found out that something called angular momentum is a vector quantity, and the angular momentum does lie in the direction of the axis of the rotation. And then they realized that if the particle is going this way, by right-hand rule, your fingers curl this way, your thumb points in the direction of the angular momentum vector. We know that there is something distinguishable that does exist because of the rotation, okay? If it had been going this way, then this vector would be pointing down for physics convention. So angular momentum is a very important thing because as soon as this starts rotating in a ring, just like a bicycle wheel, you get an axis of rotation vector quantity. They call it angular momentum. In the quantum world, they're going to start saying that we have to be careful about taking this image a little too literally, especially if that was an electron in a, 20, 30 nanometer circle, whatever. Be very careful. We can't say that this, like a wheel, is so specifically exactly that way. Because we know that this particle, when you're not interacting with it, it spreads itself out, and it's a much more complicated thing that we don't fully physically understand yet. But they have proven, if we model it a little bit this way, that there does exist inside that atom or cage, if there's a rotational thing going on, it's electron, some kind of vector quantity, arrow thing, does exist. So they're going to call it the angular momentum of this little electron, for instance, on this trap, which is a ring. So in this model, if it's moving, you will have an angular momentum related to classical terms. You're going to have a vector quantity pointing up or down. There will be a directionality associated with it. And they have experiments in different ways to kind of probe for that. Okay? So the other thing that's interesting about this is you're going to have... I'm going to jump right to the boundary condition. So one of the things about a particle that goes around a ring, you could say it goes from 0 to 2 pi. 360s is one thing. So let's cut this ring and stretch it out flat, and we'll track what it's going to do from 0 on its way to 2 pi. And we always know that we call it a wave function because the mathematical function we're going to choose, often, it doesn't have to be perfectly like this, but for this model, we need a wave-like math function. But we notice something. If I drew it in this way, just arbitrarily, we started here, and the wave function, when it reaches 2 pi, because it's a ring, it's going to start over here. And on its second circuit, do you see how the wave function is now, it's almost like it's double valued, right? And that makes no physical reality sense. That would be like saying you are actually existing in the same place, arguably at the same time, you are double valued. It doesn't seem to make physical sense. So part of our massaging process of finding an acceptable wave function, this is where the boundaries are going to dictate to us what is acceptable for the wave function. So we need it to somehow squiggle and come right back up to where it started. So now we're saying to ourselves, okay, from 0 to 2 pi, 360 is one revolution. The wave function has to go through the appropriate integer numbers of wavy thingies so that it ends here, which means it's starting here again. It's almost like a standing wave. It's never going to be double valued. So that's one of the postulates. So the birth of another quantum number is we're looking for a wavy type thing, and the wavelength symbol simply means from, from here to here, could be from here to here, could be from here to here. That's the wavelength of the wavy thing. So we need integer numbers of wavelengths, to be in 2 pi r, which is the circumference of the ring. There's your quantum number, the birth of yet another quantum number dependent on the boundary condition, the constraint, the box, the ring you put it on. So the wavelengths of our function have to fulfill this. They're going to call this quantum number, they're going to call it ML, for kind of obvious reasons that they're sort of doing it on purpose in a lot of intro books, simply because this type of rotational type of classical modeling will yield eventually in the hydrogen atom the ML number that you've already learned in high school. So we have that, and it turns out that quantum number is allowed to take on values of 0, plus or minus 1, plus or minus 2. So if the quantum mechanic math process spits out particle on a ring, what is the significance of 0, plus or minus 1, plus or minus 2, and on we go? What's the significance of that? And the energy of the allowable states will be your quantum number, h squared bar, to, and I is inertia. But the point is, this is your quantum number that you can count. So once you've chosen the particle, its inertia for the radius of the ring will be set. This is almost like constants for the system. You change this number, you change the energy state. Well, how can this quantum number be plus or minus? That is related to, if it's going this way, this vector quantity that is in there is pointing up. If it's going the other way, it's pointing the other way. So there's two values related to the rotation that we're sort of modeling of the particle. That's why it's double valued. This refers to the direction of the rotation, and hence the direction of this arrow, if you will, this vector thing that will exist. The wave function for this one, as it turns out, and we don't really need to know it, but in case you're wondering, so the formula in a box, the subscript is the quantum number, 1 over 2 pi, E, imaginary number, ML phi. And that stands for the angle of the rotation, right? And then the quantum number, ML, equals 0, plus or minus 1, plus or minus 2. So just like the particle in a one-dimensional box had its accept 1, and there's many ways you can do it. Mathematically, you can express this as something else if you wanted, but particle in a box had its own wave function and its own quantum number n. Particle on a ring, rotational type thing, has this one and its quantum number. So now what we're going to do is we're going to move on to where we wanted to get to. This is where I have to be a little more careful. Let's go to a three-dimensional particle on a sphere. And the particle here, folks, could be, you could have an electron, you could have a hydrogen atom, you could even say, hey, why don't we even look at a methane as if this was our particle? So when you put some kind of mass thingamajiggy on a sphere at that level, okay, so you're going to have this, it's a sphere, whatever the heck that thing is, you're going to keep it a certain distance, r, from the center. Now for us, much like the hydrogen atom, we all know where we're heading, folks. We want to eventually talk about a proton. Somebody takes one electron and they throw it around the proton. We want to get to the hydrogen atom. So you can see that the value in this is, if we're going to put an electron on a sphere, we're simplifying our life because this radius is going to be held constant. So what kind of spread out electron density will exist if I put an electron on a sphere, constant radius? I don't have to worry about the radius. When later the solutions to the hydrogen atom are done, you're going to have this radius distance issue of the math, which gets much more complicated, but it's solvable. But what's interesting is we hold that radius constant on the sphere, put the electron on it, and we're going to end up with two of the very important quantum numbers for the hydrogen atom. They're going to be essentially very, very, very much similar and the same. In fact, that's why we're going to use the same sort of symbols for them. So what's interesting here is this. What we already talked about, the angular momentum when you had the electron moving in one direction, creating angular momentum, okay? This was our ring. One of the analogies that they realized is when an electron is trapped on here, we don't want to say directly that we're taking the ring itself model and putting it on here, but when the electron is set loose on here, apparently Mother Nature is going to dictate, this is your new boundary. She is going to quantize certain things. And one of the other things that you'll read in quantum mechanics later is it seems as though nothing ever sits still. Nothing ever stops changing, right? Even the wave function in the system, the magical oracle thing, in time, it might settle into a reproducible pattern, but they're saying it seems like there's something about the system itself that's constantly doing what it's doing. It doesn't sit still. So the idea that comes up in here is this. It's as if the electron takes on some kind of motion that does appear to be a little bit like this. So you can have an electron, maybe I should rewrite this a bit clearer. This is your sphere. So let's just say one example is the electron happens to be almost doing some kind of rotation. Whether it's the electron literally itself or bing, 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 when you've already learned about, for instance, in the hydrogen model, a 1s orbital, right? Well, this orbital itself and the electron in its spread out sense, or the p orbital. Do you see how this does have some kind of axis? So any kind of electron, whatever its motion is, they know darn well there does end up being some kind of vector quantity that seems to be related to some type of motion of the orbital, for instance. So one of the ways they're going to make a little quick model of this is they're going to say, let's just sort of say that some aspect of this electron on the sphere ends up creating a vector-like quantity, and we're going to call it, they're going to end up calling it essentially like they did here, the orbital, the electrons, angular momentum it's somehow creating. So using the terms a bit loosely, but they're definitely saying we know that there is a distinguishable vector quantity of the electron on the sphere. So to represent this, let's just say it's doing this, and it creates this angular momentum vector. Well, it turns out, as they proved when they worked out the solutions, that Mother Nature is going to say, you know what? You're only going to allow to have specific orientations of this. So something about your motion creating a vector quantity. The direction of that vector quantity, I'm going to quantize it. I'm going to tell you you're only allowed to have certain values. So that's one of the biggest things. So it comes up with two numbers. So the wave function, when they were massaging it, came up with two quantum numbers, L and ML. I'm not going to show the birth of them specifically because the math is a little more complicated. I'm not that comfortable with it, but you can look it up and you can find that when they solve an acceptable wave function for this system, lo and behold, it works out like this. L can take on quantum numbers like this, and then the ML quantum number is directly related to it in this model. And the ML number is allowed to take on values of the negative value of L up to the positive value of L. And then the energy states, the formula for the energy of the allowable energy states is related to these two numbers. I'll dig it up. in here somewhere. Find it. Okay, so what's going to happen is, for example, let's say that we start with the very first allowable energy state that will be related to L equals 0. ML is allowed to take on values of negative L to plus L, and because this is 0, this is just 0. So it turns out that this ML number in this system, it is related to the number of states and their orientation. So in other words, we start with this one, the very first energy state. So the lowest energy state, which we would say is L equals 0, ML equals 0. You draw one stick, there's one state, and it starts there. Okay, let's move on to the second state. Well, that means you go up 1, L equals 1. Okay, ML, therefore, because of this rule that the boundary conditions in math said this must be what it is, I can take on negative 1, and you count by integer numbers up to plus 1. So this now says, in the world of energy, allowed energy states of this system, L equals 1, you're going to have 1, 2, 3 states. And each one is going to have its own orientation related to this angular momentum type of vector. So whatever the heck it is about the electron, don't take this too literally like we're saying it's literally the electron on a ring moving. No. What we're saying is something about the electron, even in whatever its spread out electron density looks like on this whole ring, whatever that may be, it does create a vector quantity. And the orientation of this vector angular momentum, orbital angular momentum quantum vector is very important for the ML. And this says there'll be 3 orientations. So this will be here. Now, if we go to L equals 2, ML is going to have to be negative 2, negative 1. Boy, this is looking really familiar, isn't it? Don't you already know these rules for the hydrogen atom? We called it the orbital angular momentum quantum number, and this is the magnetic, was it the magnetic quantum number? But it's related to L. Okay? This looks like d orbitals. Boy, this looks like p orbitals. This looks like an s orbital. And these rules we're doing right now end up being directly related to what the hydrogen atom will adopt these angular types of quantum numbers. It will. Similar rules. So now you get 1, 2, 3, 4, 5. So you might get the negative 2, the negative 1, the 0, the plus 1, and the plus 2. 5 allowable energy states. Each one has its own specific orientation and shape. The probability density of the electron when you leave it alone over the sphere will be what it is. But like nothing ever stands still, whatever the heck that whole electron density is doing, moving however that's even possible, it does create an existing vector quantity. And they're going to call it the orbital angular momentum, okay, of the electron and its distribution, however that ends up being. So you can see how useful this is. So now what we're going to do is we're going to talk a little bit more about the shape. So it turns out, and now I'm going to have to make sure that I have the appropriate So this is what they're going to do. They're going to call this, I think they call it space quantization. Okay. Particle on a sphere. So let's do L equals 2. And thus ml equals -2, -1, 0, +1, +2. I'm going to draw a picture of what an example of a picture, if you will, to try and represent some of what seems to be going on. So let's say that we create a z-axis just for us to have some reference. And let's say that we start with this one, okay? In the L equals 2 energy states, and each of them will be degenerate. We've already said 1, 2, 3, 4, 5, and this is the energy thing. If there's no magnetic field present, these are going to be degenerate. The actual energy states will be degenerate. We know there's 5 of them. So if there's no magnetic field, we can at least talk about the orientation. So let's say that you have some particular vector that we call J. And it has a particular orientation to this z-axis we're just arbitrarily putting in. Okay. And so this would be the +2. And what it's basically saying is, if we turn on a flashlight and we cast a shadow of it onto the z-axis, some books will call this JZ. Other books will say that this is related. It is related to the ML equals +2 number. Right? And this is where they will say, and notice how I said it's related, right? And others will even say it's LZ and things like that. It's related to it. But the projection, do you see how this length of the Z component gives you an indication of how the orientation of this is? Because the more I turn it away from the Z, the less and less the Z projection gets. So it's almost like the Z-axis projection gives them an idea of this thing's orientation. Okay, that's the key. So then if they were to go to the ML equals +1, turns out that you're going to rotate this further away. Like this. So the Z component is smaller, right? Then we go to this. When ML equals 0, you're basically saying, so do you see how the ML number itself is actually related to this thing's orientation? The bigger this number gets, the greater the Z projection of this thing gets. And there is a relationship between this number and the actual magnitude of it. And they have formulas for that. But we can at least see qualitatively what's happening as you rotate this away. So this one, and this is your z-axis, so if J was 90 degrees, you have 0 projection. So that tells you it's 90 degrees to one of the axes we are relative to. And if we continue on, this will be symmetrically. As soon as you do a -1, what it's saying is it's the same angle but down. And its projection here is now like the -1 version of the +1. And then when you go to the -2 one, the -2 one, you get its projection. So this is the ML equals -2. Okay? So is everybody okay with the idea, particle on a sphere, depending on its allowable energy state, the way that the electron distributes itself, like an orbital, electron density around the sphere, but yet some aspect of it can never stay completely still. It somehow does generate what they're calling the electron's orbital angular momentum, and I'm just calling it J. On the internet, maybe they use a different symbol. One step further, so the number 2 gives you an indication of the shape of the electron density. But furthermore, the second quantum number, ML, tells you how many different states will exist, okay, and their orientation of this vector related to the electron density orbital itself has specific orientations, okay? If there's no magnetic field present, then those 5 energy states are the same energy. And this is what I really needed to touch all this up with, because what's ironic, if now we put in a magnetic field. So let's say we create a strong magnetic field. We take that electron on a sphere and we stick it in the magnetic field. What I can say is, well, now I can just add it to this. So now it's almost like I'm saying, if now we put it in a magnetic field, something happens. First of all, if you have, this is a note in physics. If you had, let's just say you magically did have a charge, something with charge, when it moves, it does create an associated magnetic field itself. And even if you imagine something of a -1 charge, even if this thing was rotating itself, to see how you still have some kind of, if it's rotating itself like the Earth on an axis, you will get a north and a south pole. So now we're talking about something that's a little bit new. If this thing is rotating, does it create its own related angular momentum vector? Yes, it does. But does it also create what's called a magnetic moment? The idea being a north and south pole. And here's the thing, is the magnetic moment related to rotating angular momentum? And there is a relationship. In fact, I have a piece of paper over here that does relate. I pulled it off the internet just to yeah, so the magnetic moment, the formula for the magnetic moment, so magnetic moment is related to angular momentum in whatever the formula looks like. So folks, I'm not going to show the exact details, but what I'm going to say is this. It's only because something that's charged, undergoing some kind of if it's creating an angular momentum style vector, you are also going to have some kind of related magnetic moment. So it's almost like the two are kind of tied together in a way. So what that means is, if you're in a magnetic field, think about it. If I all of a sudden now put in a giant magnetic field, and the north is this way, there will be a relationship. As soon as you have an angular momentum vector and its orientation is this one compared to the field, to see how this one, the magnetic moment that is related to this, I'm not going to show you the exact details, but the magnetic moment related to this will interact with this magnetic field. These cannot any longer be the same energy ranking. So this equivalent energy when there's no magnetic field can't be the case, because there will be an associated magnetic, if you're in a magnetic field, you get the magnetic moment associated with the electron density. And that is related to this angular momentum. Notice I'm saying related. So these will no longer be the same in energy because of a related and associated magnetic moment related to the the angular momentum. So all of these orientations will have some kind of relationship to the orientation of the magnetic moment of it, the orbital's angular momentum. Now, this should give you and that's why people will end up calling this the magnetic quantum number. It tells you a couple things. How many different orientations of my angular momentum vector am I going to have? They will be energy degenerate if there's no magnetic field present. Take it, put it in a magnetic field. Oh, there's a related magnetic moment that is associated with this vector, which was angular momentum. And thus, these orientations will give you different energies. Now there'll be different energies. Okay? So that's kind of crucial, but it sort of tells you, and you can see how this would be, because if this thing had, and to be honest, I don't know whether this end of the angular one somehow closely, the exact orientation I don't know, but whether this is sort of northish or this is northish, who cares? But the point is, you can see something about it becomes a little bit like a bar magnet somehow, and its orientation to this will be very important for energy. Okay, so we have that, but we're not done yet, because before I finish this, we now have to handle something called the magnetic spin number. Okay, so we just sort of tidied up, in a way, the particle on a sphere. We've already noticed how those two quantum numbers is very much directly relatable to the hydrogen atom model. Okay, we know that L and ML are there. They seem to be following the same damn rules. When you do the full treatment on a hydrogen atom, you're going to end up with N, L, ML. And then these are orbital related quantum numbers. And then kind of off to the side, you have the spin one, which if you're an electron, you can be plus a half or minus a half. The analogy for this one is, and this is where I'm going to bring the idea. So now what we're doing is, I'm going to the hydrogen atom. We've already seen what can be done for these two in the particle and a sphere model. We know that is very similar to what's happening here. So now we have a proton, and you got some damn electrons, floating around it, and depending. So now you're saying to yourself, oh, we have 0, 1, 2, 3. These are the popular ones where this is S orbital, P, D, and F. And this one is just spherical. This one has this shape, but its orientation can be 3 different ways. This one has a lot of them looking like this. There's one with the donut and the thing in the middle, but there's 5 different. And each of these orbitals, this is orbital angular momentum. And the ML tells you more about how many and the orientation of them. This one has no specific orientation. There's only one of them, and it's perfectly spherical. So, I mean, there's no preferred axis of rotation for this one, really. But these do, whether you have it facing this way, or coming out, and vice versa. Okay, so now we have an interesting other problem. So let's look at the P one. So you have this. Now we're going to sort of classically model this a little bit, even though we know the electron density when it turns field-like. We're not 100% sure exactly the physical interpretation of it. But, so if you have whatever the electron density is of, say, let's say a p orbital, and remember that this is the 90% line they draw in. If they showed you every last one, you'd still see some hit and misses out here. Okay, there'll be almost like a nodal plane here, but the overall orbital in its entirety, not just the 90% line, whatever that electron is in field-like format, it's going to have with it. Do you see how you have a certain amount of almost looks like some kind of directionality, some kind of vector-like quantity? That's the orbital's angular momentum. But the electron itself, and you look how big this orbital actually can be when you full 100% of it, right? This is the bulk of it, 90% of it. But now, and I'm just going to kind of cheat a little bit, I'm going to draw a picture of the electron for itself, just for a moment. We take a measure and we find it here. Even though we know what spread outness is this. The orbital has an angular momentum thing related to it, but so does this. So the classical model is, let's pretend that the electron itself, if it's rotating, so it's rotating somehow, it can create its own angular momentum type of vector quantity. We're going to call this one, they called it spin. They'd like to get rid of it, but they're saying is there's an intrinsic angular momentum type of vector quantity thingy that the electron itself has. The orbital of the spread out electron density has its own angular momentum vector thingy. But so too does the electron in isolation, if you will, in more of an isolation, so to speak, has another little vector. So you've got a bigger angular orbital momentum vector. You've got one here that they've called spin. And notice what they're going to do here. Each one, so when we had L and ML, orbital angular momentum, and this is the electron orbit's orientation, the corollary is just like L. Now when you're talking about this thing spinning, creating a vector that's angular momentum-y, we'll call it S. It's just kind of like that. And then the projection boop, 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 on the Z-axis, that's the MS related, MS, just like ML was like related to the projection, so to speak, than the MS is. So in other words, what they're saying here, if you had your Z-axis and you had a little angular momentum related vector, because this is spinning but not literally, so we'll call that S, the projection on here, SZ, if you will, that is related to the MS. So in other words, for an electron, what they're basically saying is it can only be oriented, so the MS is this component of the angular momentum pointing up, so this is plus 1/2. This one will be the diagram of the MS equals negative 1/2, because the projection of S, right, gives you this quantity, the Z component of it, and that is related to the quantum or MS negative 1. So there's only two orientations Mother Nature has allowed for this intrinsic vector quantity of an electron's spin. So now what do we have? Wow. In physics, classically semi sort of model, just for a moment, is now you're saying you got the whole damn orbital creating some kind of orbital vector thing, call it J. Then you got the electron itself, in some way, has its own littler, usually littler, angular momentum little vector thingy with, with it. We call that S. Well, these two can probably couple together to give you total angular momentum. So somehow you add these two vectors together and you get some bigger total angular momentum. I'm just going to call it total angular momentum vector. But this even does change with time as it gets a little more complicated. Okay? But don't panic. The electron itself intrinsically has an angular momentum-y type of vector thing. The orbital distribution of the electron itself also has an angular momentum thingy. So now you get these interesting images that look like this. Not to confuse it too much, but let me see if I can. This one's pretty good. So what they've done here, let's see if you can see this. This came off of Wikipedia. And Wikipedia is free. That's why I'm plugging it. And I do try and donate when I can to it. I really like Wikipedia. So notice what they've done here. Remember that little vector I showed you here? So what they're saying is the projection, let me back out because this is kind of important so I can finish this. See that little vector here? Imagine Z, let's just say you had a vector. It doesn't matter whether it's the J or the S. But imagine in the X and the Y direction that this vector sort of precesses around. We always know the projection on the Z-axis, or we could if we opted to. But what that means is we don't know where the shine a light down on the X or the Y is. We don't know where that is. So you get what's called a cone. What this does is show you the orientation of the angular momentum E vector in its projection on the z. But if we know that, you're not going to know the component down on the y or the x, and therefore you get this weird spread out somehow weird vector thingy looking like a cone. So that's what they're saying here is if you have the orbital angular momentum, now notice what they've done. They've used L. So this is their orbital. That would be like what I called the J vector because of your orbital angular momentum. They called it L. But see how it has this bigger cone. But if the electron itself has associated with it its spin-related angular momentum-like thing, its projection on its z-axis, but has that cone, the two of them can couple together to give you what they're calling J, the total angular momentum, which is this bigger cone. And that's what I suggested. You could add these two quantities together to get the total angular momentum cone and its projection right here on the z-axis. This is called the spin-orbit coupling to give you the total. But you can see how important it is to have these quantum numbers that give you an idea of the orientation. Okay? So I think I've summed that up. But I want to reiterate one thing, going back to this. When we were talking about the orbital angular momentum only, we didn't have the spin one yet. These angular momentum vectors of the orbital and their orientation, which is related to ML, it's the orientation that ends up showing itself, making the energy states different only when you put it in a magnetic field, because the angular momentum does have a related magnetic moment. So we're not going to go into those details, but you do understand there will be a relationship between something about this directionality and the magnetic moment the orbital itself can have, the electron as well, right, from its spin. So you're going to get the total magnetic moment, if you will. So when you stick it in the magnetic field, the exact way these energy states end up staggering themselves is related to that. I think, folks, that's a pretty good treatment of taking you through and keywords mentioning how the process of getting to the quantum number, you have to use, and they have a much more bigger list of quantum postulates, things that have to be satisfied. That's how you massage your math function as you're trying to find an acceptable one for the boundary condition of the trap or the box you're using. The answers are phenomenal when you choose a really good wave function, which is a math function holding the information that's observable.